Welcome to the 400 level session, Get Deep Insights about your machine learning models during training. My name is Natalie, I'm an applied scientist at AWS, and I'm very delighted that I'm going to present this session together with Chaim, who is a machine learning algorithm developer at Mobileye. Let's have a brief look on the agenda. In the first 5 minutes, I will give a high-level overview of what Amazon SageMaker Debugger is, and then I will jump straight into the demo where I will show you how you can use Debugger to find critical model bugs, improve resource utilization, and reduce training time and cost. Then Chaim will take over and show us how Mobileye has used SageMaker Debugger to improve state-of-the-art instant segmentation models. So what is Amazon SageMaker Debugger? Debugger is a feature that we have launched at reInvent 2019 that allows users to automatically capture model data, tensors from the model training. We have modified the SageMaker DLC containers in a way that users do not have to modify anything in their training script nor in the model. When you start your SageMaker training, you simply specify which kind of tensors you want to have emitted, tensors such as weights, biases, gradients, and Debugger will take care of the rest. This year, we have extended the capabilities of Debugger to not only capture model-related data, but to also capture performance data, such as utilization per CPU, GPU, I/O, network, and memory, and to also capture performance metric from the training script itself, such as data loading, preprocessing, operators running on CPU and GPU. Debugger comes with a set of built-in rules, and that allows you to automatically identify issues in your model training, such as overfitting, underfitting, vanishing gradient, and many more. This year, we have extended the set of rules with a whole new set of rules that can now identify performance-related issues, such as CPU and I/O bottlenecks, and many more. You can also use Debugger for real-time monitoring, and that is especially useful if you have training jobs that run for several hours or even days. Debugger will emit the data in real time to Amazon S3, so while your training job is still in progress, you can already start fetching the data, visualize and analyze the data. Now you can also monitor the utilization in real time and profile your training by step or time duration. All this together allows you as a user to save time and cost because you can find issues early in the prototyping phase, accelerate prototyping, and with the performance data, you can now identify the right size training instance, improve resource utilization, which directly translates into cost reduction. Debugger is integrated in SageMaker Studio, so you can use Studio to get alerts about the built-in rules. As well, you can use Studio to visualize the performance data. Training machine learning models is difficult and compute intensive, and as an applied scientist, I know those pain points just well. Whenever I would create machine learning models, I would do it in an iterative process where I would try out different hyperparameters, different model architectures, different data sets and preprocessing, and quite commonly I would find myself in a situation where I would end up with a model that starts overfitting, underfitting, or maybe just a model that does not generalize at all. And trying to find the root causes of such problems is not always easy, and for sure it's very time consuming. When we do machine learning model training, we typically train those models on large compute instances because we have large data sets. Especially when we train deep neural networks, we train them on GPU instances, and trying to use those instances as efficiently as possible is not always easy. But given that training machine learning models typically takes a long time, we want to ensure that we use the resources as efficiently as possible to reduce the training time. And now I would like to jump to the demo where I will show you how you can achieve exactly that with SageMaker Debugger. So let's take a look. In this notebook, I'm going to take a pre-trained ResNet model from the PyTorch model zoo, and I fine-tune it on a new task. The new task is to perform traffic sign classification. The model is achieving a decent test accuracy of 92%, but nevertheless I decided to run it with Debugger built-in rules enabled to see how well is it actually training. To do so, I use now the SageMaker Debugger module and I select the rule config subpackage. Rule configs allows me to access any of the available Debugger built-in rules. Debugger can capture any kind of data from the model. So it captures, for instance, the model inputs and provides built-in rules to identify dataset-related issues. Debugger can capture the gradients and provides rules that can identify issues such as vanishing and exploding gradients. The vanishing gradient problem is illustrated here in the animation, where we can see that the distribution of gradients is somewhere in the order of 10 to the power of -8, -7, so really small. Debugger can also capture weights and check for issues such as poor weight initialization. And for activation functions, it, for instance, checks for neuron saturation. If you have too many neurons in your model that suffer from this type of problem, then your model cannot effectively learn. Debugger also checks for issues such as overfitting, underfitting, or simply the training not converging at all. And these are typically scenarios where you want to use Debugger to auto-terminate your training job, because trying to train a model that just does not generalize would be wasted compute time. As I mentioned in my introduction, Debugger can now also capture performance-related issues, such as CPU and I/O bottlenecks, workload balancing issues, and many more. And when we look at the machine learning training pipeline, how this typically looks like is we start with a set of data that is available in a certain file format. The data has to be read onto the CPU RAM, where the data preprocessing is typically happening. The CPU prepares the data batches that are sent over to the GPU. The GPU performs the training, and then there is synchronization happening between GPU and CPU. Your training may run into the situation where it's suffering from a CPU bottleneck. What this means is that the GPU is now waiting for data to arrive from the CPU, so the utilization goes down, and the CPU is very busy with preparing the data for the GPU. So the utilization on the CPU is very high. You would want to avoid such a situation because it leads to GPU underutilization. Now I'm selecting the built-in rules I want to run my training with. I select here class imbalance, date reload, and loss not decreasing. And for all these rules, I can on top of that specify rule parameters that allow me to tweak the rules for my specific use case. Next, I specify the performance-related rules. I select here the low GPU utilization and the profiler report rule. What the profiler report rule does is it will run all the performance-related rules and create a final output report with recommendations of next steps. Next, I specify the debugger hook configuration, and that tells debugger which kind of data to save from the model. I can either use default collections such as weights, biases, gradients, but I can also very easily customize my own collection. In order to do that, I just need to specify a regular expression of the tensor names I want to have included in this custom collection. Now I specify the profiler configuration. Here I specify a sampling interval for the system metrics. I set it to 500 milliseconds, and I specify a configuration for the framework metrics. The framework metrics are those metrics like data loading, preprocessing, operators running on GPU and CPU, where I basically tell debugger when to capture this data and for how many steps. What debugger will do, it will now take the system metrics, such as, for instance, the GPU utilization, and correlate it with what has been happening in the training script. So, for instance, when I see that my utilization goes down to 0%, I want to know what has been happening at the same time in the training script. I can see here the data preprocessing was happening. So that gives an idea of the potential root cause of the drop in utilization. Now I'm ready to start the SageMaker training. I define a PyTorch estimator object where I pass in my training script that has the fine-tuning of the ResNet model. And in the estimator, I just have to specify now all these configurations that I defined previously. Now, when I call estimator fit, what will happen behind the scenes is SageMaker will spin up the training container where it will run my training script, and Debugger will take care to automatically emit the data to Amazon S3. SageMaker will also automatically spin up the rule containers. Those rules will run on a separate instance, so they do not interfere with the training. They will fetch the data from Amazon S3 and perform the analysis. And as a user, I run those rules for free. I can now use the SageMaker Python SDK to get information about the rule status, but I also can go to SageMaker Studio and the experiment view to get some more details. So what I see here now for my training job, I see all the rules that I'm running, and I see that apart from the date relu rule, all the rules triggered. So now it's time that I want to use Debugger to get deep insights into my model to identify what has been happening there. In order to do that, I install now the SMDebug library. It's an open source library that provides all the utilities and functions you need to access and query the debugger data. The first step is always to create a trial object. The trial object takes the path to the debugger data, which can either be an S3 path or a local path. Once I have the trial object, I can start accessing and querying the data. Now I'm interested to identify why did the losses not decreasing rule trigger. I use now the function trial.tensor, where I simply have to specify the tensor name I want to retrieve. In my model, I have used the cross-entropy loss function, and Debugger has stored the inputs and the outputs. And I access now with dot values all the values that Debugger has recorded through the entire training. And this dictionary is automatically updated as the training is still in progress. So now I see with just a few lines of code, I can plot the loss curves, and I see that after 1000 iteration, my loss did not decrease any further, and that's why the rule triggered. So obviously, I have been training the model for too long. Now I want to investigate why the class imbalance rule triggered. Now I'm not just taking the outputs of the loss function, but this time the inputs. The inputs into the cross-entropy loss function are the labels and the predictions. And now I'm taking the labels to count how many class instances has my model seen through the entire training. Therefore, I specify modes.train as for the training phase. With just a few lines of code, I get some interesting insights. On the x-axis, I have the different image classes that my model is trained on. And on the y-axis, I have the counts of samples that the model has seen. I see that some image classes the model has seen less than 50 times and others more than 250 times. And that's why the class imbalance rule triggered. Now I was curious to see if, due to the class imbalance issue, whether there were certain image classes that the model predicted more often incorrectly than others. In order to identify that, I use Debugger to get the model inputs, predictions, and the labels, and I just check where does the prediction not match the label, and then plot the image plus the prediction and the label. With just a few lines of code, I get some interesting insights where I quickly see that my model always does an incorrect prediction when it has to predict a direction, like keep right and keep left, turn right and turn left. And that is a severe model bug, and I would be very reluctant to deploy such a model to production, even so it reaches a decent test accuracy of 92%. The root cause of the issue here is that the user had applied a random horizontal flip during the data augmentation, which is typically used when you train ResNet models, but it's causing a problem in a dataset like that. So now that I identified model-related issues, it's time to look into the performance data. I have seen that the low GPU utilization rule triggered. Debugger will create profiler reports, which I can use to download and get some further insights. And I can also use Studio to visualize the data and get further insights. Studio shows in the beginning an overview where I get some high-level information such as the job duration, which was in my case 2,200 seconds. The initialization took roughly 15%. Then I get a utilization summary per worker node. In my case, I only have been running on one worker node. And I see, for instance, that the median GPU utilization was only 50% and it never exceeded 91%. So obviously, I have been underutilizing the instance. Studio then also shows me the resource-intensive operations listed by the cumulative time on the GPU and CPU. And then I get an overview of the built-in rules that have been run by the profiler report rule. I see, for instance, that the batch size rule triggered, low GPU utilization, and a step outlier rule. I can now get some further insights into the data. I see here, for instance, that the CPU utilization over time never really exceeded 25% utilization. And when I look at the GPU, I see that it never really exceeded 60% utilization. So obviously, I have been underutilizing the training instance. I can now go to the profiler report to get some further insights. The profiling report gives me, in the beginning, a very high-level, similar high-level overview like Studio. I see then a rule table summary with some description and recommendations. And for each of the rules, there will be some further analysis. So for instance, the step duration analysis shows me that on average, my step time was 0.04 seconds. However, the step outlier rule triggered because it identified a few outliers. So I can zoom into my step duration histogram. And now I see that there were some significant outliers. What Debugger will do, it will take those outliers and correlate it with what has been happening at the same time in the training script to get some further insights. The profiling report also includes some more information about the GPU utilization analysis, like box plots and workload histogram. It also includes a data loading analysis. In my case, it reveals that my training instance provided 8 CPU cores. However, on average, I was only running 1 data loader. So obviously, this could have been improved. Then the report also shows me that I did not use pinned memory in my training script. In the case of PyTorch, I can easily enable that by just specifying pin memory equals true in the data loader. The report also shows me a histogram of the data loading times. And then the batch size rule shows me the overall CPU utilization and the utilization on GPU as well as for the GPU memory footprint. And what I can see is my utilization on the GPU never really exceeded 60%. On the CPU was also very low utilization. At the same time, I see that my memory footprint is very small on the GPU. So that tells me that I could have increased the batch size, which means I would increase the memory footprint on the GPU. And because this GPU does more processing of more data, also the utilization would increase. So based on all these insights, I can now go back to my training script and start correcting the training script. The first thing I do is I minimize the number of epochs because I have seen that the loss is not decreasing rule triggered. So I decreased the number of epochs to 3. I have seen that there was a class imbalance issue and I can fix it with weighted resampling. So when I load the data, I will apply weights so that my data loader samples more images from classes with fewer counts. Then during the data loading, I also increase the number of subprocesses and I apply pin memory. Then for the batch size, I increase now the batch size from 64 to 264. And now I rerun the training and I can check in Studio the status of the rules. What I see now is that some of the rules are no longer triggering, such as class imbalance and loss not decreasing, but low GPU utilization and profiler report rule still do. I can now go to Studio and investigate why they still trigger. First, I see in the overview panel that my training time reduced significantly from 2,200 seconds to 800 seconds. I see then in the utilization summary that my median GPU utilization is only 0. That's partially because I spent now more time in the initialization and less time in the training loop, but it's going more often now also to 100% utilization on the GPU. I can see in the rules that batch size and step outlier rule are no longer triggering, but low GPU utilization does. So I can now go to the node overview and I see here my CPU utilization increased quite a bit because I have more data loader subprocessors. And when I look at the GPU utilization, I see that it's now going more frequently to 100%, but sometimes it's dropping to 0%. So it seems there are a lot of fluctuations in the usage, and that's why the low GPU utilization rule still triggers. So it seems there's still some further room for improvement in terms of performance. Nevertheless, if I now look at my final model accuracy, I see that I reach now 94% test accuracy versus 92% in my initial training job. So SageMaker Debugger has helped me to increase model performance, to find a critical model bug, and to reduce training time by more than a factor 2. With that, I would like to finish the demo and hand over to Chaim, who will now show us how Mobileye has used SageMaker Debugger for their instance segmentation models.
Hi everyone, my name is Chaim Rand. I'm a machine learning algorithm developer at Mobileye, and I'm happy to be here with you today to tell you a bit about how I use Amazon SageMaker Debugger in my daily development. In case you haven't yet heard about us, at Mobileye, officially known as Mobileye, an Intel company, we are in the business of making roads safer. We are a global leader in developing technologies for driver assistance solutions and autonomous vehicles, and as of today, there are over 60 million vehicles around the world containing our technology. Let me give you a small taste of the kind of stuff our algorithm developers work on. A key component of autonomous vehicle systems is the ability to identify road-related artifacts in its surroundings, including vehicles, pedestrians, bicycles, and more. We refer to this capability as autonomous vehicle sensing technology. One way to do this in a system based on standard RGB cameras is by segmenting each incoming frame into object regions in a process known as semantic segmentation. Each pixel is tagged with a label indicating whether it is part of the road, part of a car, part of a pedestrian, and so on. While semantic segmentation tags each pixel with an object type, autonomous vehicles need to be able to distinguish between different instances of the same object. They need to be able to solve the problem of instance segmentation, in which each pixel is tagged with a label that uniquely identifies the object it belongs to. In fact, autonomous vehicles need even more than that. In order to safely make decisions about its next steps, what trajectory to take and whether to brake or accelerate, they need to be able to track the location of each object in a sequence of frames in order to understand its motions. In other words, the instance identification needs to be consistent across frames, as shown here. One of the ways to develop a solution for instance segmentation is by training a deep neural network. At Mobileye, many of our algorithms rely on training deep neural networks. We train these in the cloud using the Amazon SageMaker service. SageMaker provides us with a solution for training on extremely large datasets, which we store on Amazon S3 and stream directly into our training session using SageMaker Pipe Mode. By using SageMaker, we can run as many training experiments as we want and easily scale to training with multiple instances. One of the things we have learned during the time that we have been using SageMaker is that SageMaker is a whole lot more than just a managed training environment, offering services for facilitating development of machine learning solutions from ground truth collection all the way to deployment. Perhaps none more valuable to us than SageMaker Debugger. To explain just how valuable SageMaker Debugger is to us, I'd like to share 3 significant challenges we face when training DNNs, such as the instance segmentation model I showed before. The first is the need for in-depth monitoring of the learning process. Monitoring the learning process is a critical part of DNN development, especially when training large models such as instance segmentation. We require tools for real-time analysis of a great variety of tensors, including gradients, activations, metrics, and more, in order to develop a deep-level understanding of how the training is progressing and figure out what changes to make to improve our model. The second challenge has to do with automating the management of our instance segmentation experiments. As I mentioned before, we typically run many experiments in parallel with the expectation that some of these will not succeed. Even the ones that do succeed will often require updates to the hyperparameters. Since our models are often configured to train for several days, we need to automate termination of failing jobs and reprogramming of jobs requiring updates so that we don't end up racking up training costs for no return. I'd like to demonstrate the need for this by sharing a painful anecdote based on my own true experience. Imagine kicking off a bunch of instance segmentation training jobs before leaving for the weekend, as we typically do, and returning 3 days later only to discover that the training jobs, which are still running, all hit a bug and stalled 10 minutes after you left the office. Not only have you lost 3 days of training time, but now you need to explain to your manager how you ended up racking up training expenses all weekend long without any return whatsoever. We will return to this story in a short while. The third challenge has to do with profiling the runtime performance of our instance segmentation training session. Training resources are expensive, and we are consistently searching for ways to maximize resource utilization, reduce overall train time, and reduce cost. As shown earlier by Natalie, training is a complex process which involves a number of components, and thus a number of potential types of bottlenecks. We require tools for identifying these bottlenecks and accelerating our training sequence. Let's now see how Amazon SageMaker Debugger helps me solve these three challenges. The challenge of monitoring the learning process is solved by the deep-level tensor capturing and analysis feature. Here I show a simple example of real-time monitoring in which we use SageMaker Debugger to capture the input and output tensors and process them in order to create a visualization of how both the semantic segmentation and instance segmentation evolve over the course of training. One of the unique properties of SageMaker Debugger is that it captures full tensors. This enables deep and flexible tensor analysis as opposed to having to fix how tensors are processed and displayed during the training. With SageMaker Debugger, I am free to play around with processing controls and thresholds and evaluate how these impact my predictions, potentially gleaning greater insights than otherwise enabled. The second challenge of automating management of my instance segmentation experiments is solved by the SageMaker Debugger rules. I can program rules to identify when my jobs have stopped learning and either automatically terminate them, restart them with updated hyperparameters, or take any other appropriate action. So I'm sure some of you are still feeling a little queasy from the painful anecdote I shared earlier. Fortunately, there is a happy ending. As I show here, using SageMaker Debugger, I can program the stalled training job rule to identify and terminate stalled training jobs. So I can leave on my weekend holiday and sleep easy, knowing that I am not in danger of flushing away my company's money. Last but not least, the SageMaker Profiler addresses the challenge of improving the resource utilization and reducing the overall runtime and cost of my instance segmentation model. Some of the unique features of the SageMaker Profiler are that it enables me to collect and compare a wide variety of both system and framework metrics. It is not limited to a small window of training steps, providing metrics on the end-to-end training session. The APIs enable me to control the level of invasiveness of the profiling probes, and it provides me with an auto-generated report with deep-level analysis and recommendations for making improvements. Let's take a quick look at the performance data that is available for one of my instance segmentation experiments. In this experiment, I went a little overboard with the tensor collections, choosing to capture just about every tensor in my model, and at a very high frequency of once every 50 training steps. Let's start by looking at the profiling report in SageMaker Studio. From the resource utilization section, we can see that while the GPU does reach a maximum utilization of 100%, many of the measurements are shockingly low. On the pie chart below it, we see that the GPU is underutilized for the majority of the training session, and unsurprisingly, we find that the debugger rule that is responsible for monitoring the efficiency of the GPU use has been triggered no less than 16 times. Using the Debugger Profiler analysis tools, I can now go ahead and plot a graph of the GPU utilization as a function of the training time and clearly see the strong fluctuations. Since Debugger also collects the framework metrics, I can plot the times of the training steps on the same graph. Here, I have highlighted every 50th step in yellow. By plotting the metrics in this manner, I am able to correlate between the GPU utilization and my training progression. In this case, I can see that the drops in GPU utilization coincide with every 50th step, precisely the steps in which I have chosen to capture all of the graph tensors. What I learned from this analysis is that I need to be more careful about how I use a tensor capturing feature, how many tensors I choose to capture, and at what frequency. I want to emphasize that this analysis relied on two of the unique properties of the SageMaker Debugger Profiler. First, that it enables me to collect and compare both system and framework metrics, and second, that the profiling is not limited to a small window of training steps, which may have resulted in missing the bottlenecks altogether. This brings me to my final slide. As I have shown you, SageMaker Debugger provides our algorithm developers with indispensable features for monitoring and controlling the training process. The tensor monitoring tools empower our developers to glean deeper insights into the learning process than ever before. The profiler takes performance analysis out of the domain of a few specialized experts, simplifies the discovery of bottlenecks, and helps us maximize resource utilization. And the automation enabled by the debugger rules increases our efficiency. All of which ultimately lead to cost savings and faster model convergence. Thank you.